Another example of class diagram is this car composition. Of course, you see these diamond shapes represent a strong type of relationship between the car and other components of the car. Basically, these filled diamond shapes suggest that the life cycle of car is exactly the same as the life cycle of these objects. Basically, they are separate objects because it's useful to have them implemented as separate entities, as separate concepts. However, if you want to use the car, you must have all of these things in place. Otherwise, the car will be dysfunctional and cannot be used. And of course, these multiplicity specifiers like 1 to 4, car and with 4 wheels, suggest the very direct idea or restriction about the design. So basically, you have to have 4 wheels created and a car in order to be able to use the car, and so the other parts of the car. A class diagram can have 3 parts inside the box that represents the class diagram: the class name, the data attributes, and operations or functions or procedures or methods. Depending on specific programming language, they have different names, but generally speaking, operations are tasks built directly into the object that it can perform. For example, with the car situation, you could have start the car, stop the engine, and things like that, shift gear, and things of that nature. So you can see that the attributes and operations are actually optional, but in a class diagram, at the minimum, we require the name of the class. And this name of the class, and each name of the class at the top of the box, or in our case, is just a simple example of using just the name of the class. This name of the class becomes the name of the new data type in a programming language. So directly coming from the class diagram, we know that we can create objects of type car, steering wheel, and so forth. A class diagram with all of the relationships specified can tell the whole story, because there's quite a bit of information encapsulated in the diagram. So here we begin to explore a little bit more of relationships, and in this diagram we can say that a person has a house. So these simple association relationships represent an access from one object to another in computer memory. And by the way, there's an asterisk here visible in the diagram which suggests that there could be multiple houses, multiple instances of this class in computer memory, whereas the person could have access to them. So that typically suggests that the person has a collection of references, some sort of array or some other type of collection in its memory internally that stores references to all houses that are associated with this person. Of course, you can never go against the direction of arrows, and you cannot say that house has a person, because the arrow does not allow you to do something like this. So this is association is really has a relationship. So person has a house, house has a room, but here we also make it stronger, again indicating a composition and showing in the diagram that house is made up of rooms. So basically the rooms are inherently important part of the house. Person has a room, so we can associate a specific room with the person, right? So there's no multiplicity here. That means 1 to 1. So what this arrow indicates that this object, when this class is used to create an object in memory, will have a reference or pointer to another object named room, and somehow this is important to this application. And so is with the dog. So person can have multiple dogs, which again is indicated by this asterisk, and dog also has a separate pointer back or a reference back to the person. So this is quite telling parts of the diagram that allow us to extract a lot of information important to start putting down the actual source files, the actual files which will be describing these classes in software. These are examples of associations between classes that are possible within the specification of UML, between different classes. And the first one is dependency. Dependency is not a direct association. It does not suggest that this object has access to another object. Rather, for instance, if you have a tax calculation engine object of some kind, you designed it, and you also have like a math library of some sort, which provides you a lot of functions implementing all sorts of things like standard deviations and the statistical functions, all sorts of things. So this math library may not be actually an object, but just a set of utility functions or utility procedures that the tax engine is using very heavily on a routine basis. So then the dependency here, if we provide it, like if we provide this punctured line indicating dependency of tax on the math library, this indicates basically one thing, is that if there's a change taking place somewhere here, for some reason we're making updates, we're doing some changes here, perhaps we're decided to change the types of input and output that certain functions take to do the math calculations, that suggests that it's a signal by this diagram that the tax engine may have to be revised. It will be affected by the changes that are taking place over here. So this is a bit of an example of breaking encapsulation rules, because in the ideal situation where we only have aggregations, composition, associations, these types of relationships, which basically indicate access from one object to another, in those cases, really the objects are much more independent. So if this was not a dependency example, but just simple association example, then changes in the math library class would not be directly affecting the tax. So dependency is just a signal that there is some kind of strong dependency of the implementation between one part of the system and another part of the system.